Okay, so we have, of course, our continuum of our species. So we've got a fluid and we've got the concentration or the mole fraction changing across that space. So that's the problem we've been working on, that we've got some phase, and I'm just drawing some arbitrary shape here, intended to mean in 3 dimensions. And so we've got the continuous change of our species. In other words, we could just draw some line in 3D space. And if we look along that line, if we define a distance along that line, let's just call it S. So, so far, S has been X, Y, or Z, or it's been R and Z and so on. So S is some arbitrary length. And we have been looking at a mole fraction or a concentration, and we've been looking at how that varies continuously through S. So we've been developing equations that describe how that mole fraction or concentration changes. And the way we did that was through an equation of this form, right? So like we talked about yesterday, we've been developing that we have a convection term and we have a diffusion term. And what we've managed to do so far is generalize that to any geometry. So we said that in Cartesian coordinates, of course, we have X, Y, and Z. And then in cylindrical coordinates, we have R, theta, Z. And in spherical coordinates, we have R, theta 1, theta 2. We could also imagine any coordinate system, and you could invent your own coordinate system if you wanted to. So you can propose for any coordinate system that you can translate to any other coordinate system. So if you have, for instance, the Cartesian coordinate system, and so you've got X, Y, and you've got Z perhaps coming out of the page there, then you can, of course, define any position in that space. So you can define some subspace in here, and we'll show that as a little rectangle in our space. And then you would think about how does that project down onto this plane. So on this plane, it projects perhaps like this. And then you could also project this object onto this plane. So then it would look perhaps like that on this plane, and you can project it onto this other plane as well. So you can imagine a 3-dimensional subspace, and we can define our subvolume there. So that we can define in terms of X, Y, and Z, or alternatively, we could define it in terms of R. And then the angle is what we would use in spherical coordinates, the angle in that direction and the angle in that direction. So we are always talking about the same space. We are, when we think about it, these are all objects in the real world, and then it's our choice whether we want to work in XYZ or R theta Z or R theta 1, theta 2, or some other coordinate system. So for any coordinate system, though, we can define the gradient of any function, and the second gradient, well, any gradient. We can define any order of gradients. And the point is that we can develop the relationships among all these types of coordinate systems. So for the cylindrical coordinates, the first derivative looks like this, the second derivative looks like this. And if you go back and look at what we did for the cylindrical geometry when we had flow in pipelines, right? The convective term had, or rather the diffusion term had 1 over R and DDR of R times something. And that was because we couldn't cancel the R, because the R was an R at R plus delta R and all of that. So if you go back and look at it, we had certain terms that we couldn't easily cancel out. And so that's why it leads to these artifacts here. So remember, in Cartesian coordinates, you don't really see that. It's all nice and kind of clean and neat there. But in cylindrical coordinates, because the area changes as you move out in the radial direction, then you have that bit of an artifact, and it also persists for the angle. And then in spherical coordinates as well, if you go back and look at, even when we didn't have the angular forms, we had an r squared instead. So the point is that we, with all that geometry complication, we can still identify a grad squared f or a grad f. And so we have generalized nicely all the geometry into this, and it's not merely a symbolic form. By this, we mean the first gradient of a function in all directions in that coordinate system, or the second derivative of that function in all directions for that coordinate system. So you can always define the grad operator for your coordinate system, and then that allows you to develop an equation or develop your balance without concern about the artifacts. So this equation is generally true. It works for all geometries, whether one of the three or any other one. So this equation is always valid. So that's the first generalization that we talked about. So that's a big step forward for us. The next thing we talked about was here, where we've been talking about just the mass balance in this part of the course. But of course, there is also the energy balance. And in the energy balance, we are looking at the rate of change of the energy in our space. And so if we imagine, again, some subspace, so if we imagine some space here, like so, then we will have a flow through the space. Thank you. So we have, we can write here that there's a flow into and out of the space. And as a result of that, we have a certain rate of change of whatever quantity it is in the space. So we took that approach for mass, but you could also take that approach for energy. So you can say that the total amount of energy in the space can change simply by virtue of the fact that there is energy in the stream that's entering here. And then we are also losing energy from the space as energy in the form of the chemical content that's also leaving the space there. And then that would then count as the convection analog to our balance. So in the case of mass transfer, we had U grad C. In the case of the energy balance, we have U CP grad T. And we'll talk about this in some more detail later today. Then in the mass balance, we also had diffusivity times grad squared C. So this was our diffusion part. And if we think about energy, we also have conduction. So when we have a temperature difference between 2 points, so let's say there's one temperature here and there's another temperature here, then if this is at a higher temperature, there'll be a net conduction, right? If it's a slab of metal or something, and you have a higher temperature at one spot, then then you'll find that the temperature will slowly rise across there. So initially it might be like that, but slowly those temperatures will equalize. And so you have a tendency for energy to diffuse also, or conduct. So that's conduction of thermal energy. So it's the same concept as diffusion of mass. Okay, so that's what we have for energy. And then for momentum, we can write this form. So this is on the kind of volume basis. So this is mass times velocity. It's just been divided by volume. So mass times velocity is, of course, momentum. So the rate of change of total momentum in the space, that is, of course, the force that is being the amount of force in the space. So the rate of change of the force in the space is equal to the momentum loss by convection. So we can think that when a fluid is entering here, it's entering at a certain momentum. So we have the contribution to the force here from the momentum of the stream entering. And then when the fluid leaves also, that's a loss of momentum, or rather a loss of force by momentum. So we have a momentum loss as well. And then we also have a diffusion-like term here because of the concept of viscosity. So if you have, and this is the example we drew yesterday, if you have a glass of water and if you have a glass of honey, then of course the honey is, it has a higher viscosity. It offers a greater resistance to any kind of deformation. And what it also means is that if you have a stream that's flowing, let's say it's a stream of honey here, then your stream, your center line, the fluid at the center line position, that's typically the fast position, and then near the wall is slow because of friction with the wall. But because of high viscosity, the fluid in the center line will tend to drag the fluid among its neighbors forward as well. So you will have a viscous drag of the fluid, and so that will be a momentum loss for the high velocity parts. So the high velocity region will lose momentum to the lower velocity regions. And obviously by conversely, the low velocity regions will be dragged, and so they will accelerate, or they'll accelerate. So so that is a loss of momentum due to viscosity. So again, you have this concept of a kind of diffusion. So this is in a sense diffusion of the force. Your momentum force is diffused across your space here. So that's also like another diffusion type of term. So the point of all this is that there is some relationship among these three balances. And when you read the outline for this course, it was about momentum, mass, and heat balances, as if those were separate concepts. But we can see that there is some kind of pattern behind this. And one has to speculate, what's the reason that there seem to be the same two concepts? And if you think about those concepts, it's not just that those are independent two concepts every time. Those two concepts seem to all be the same type of thing. So the concept of convection, the concept that as things move around, they carry that property into and out of the space. Then the concept that because of the neighbors of the space, we are, in a sense, distributing that property among the neighbors. So all those concepts are similar. And, here's where I'm speculating. It's not the case that this is by any means solved in physics or in engineering. It's that looking at among these, we start to realize that maybe there's something wrong with the way that we choose to count what's happening in nature, or the way that we quantify our phenomena. So this choice of working with concentration, this choice of working with temperature and with velocity, there may be some more fundamental way to express the changes in a space. And if you think about temperature, for example, that's one of the properties that really exposes how biased we are to our kind of human experience. So if you think of it, if we touch something at a high temperature, then we experience that as pain in our nervous systems, and then we say, oh, that's hot. Or if something has the reverse effect, then we say that's cold. So it's because our nervous systems are the way they are that we've come up with this concept of temperature eventually. And then by the same token, lifting things around, talking about densities, oh, this is the same size, but it's heavier. That's how we've come up with this artifact of density, and so on. So it might well be that there is some theory still to be discovered for a more fundamental way that will then merge all these concepts into one thing. But for now, this is the framework that we are presenting in this class. So that's a kind of generalization. So what we can do is say, well, they all seem to have this pattern, that there is some quantity, so we'll just call it phi. And so phi could be a vector of concentrations or temperatures or velocities. And we have the rate of change of that phi being related to a convection concept and related to a diffusion-like concept. So if you like, this equation represents all of the changes in a continuous space. And this is considered one of the achievements of the human mind, being able to describe completely all the changes that occur in a space. I will say that it's not the only situation that arises, right? If you think of it, all this is for the specific situation of a continuous fluid. So if you have some space, and if the space is completely connected, in other words, it's a liquid or it's a gas, and we are only concerned with molecular movements in that space, then this is considered a good representation, right? This is considered a good representation of the whole space. Because these objects in the space, although they are discrete, right? We think of molecules as being discrete things. Although these are separate objects in the space, we have such a crazy number of them, right? They are on the order of an Avogadro's number, right? Which is on the order of 10 to the power 23 molecules per mole. So that's an unimaginable number to us. So because you have this crazy high density of molecules, what tends to happen is the whole space behaves as if it's one homogeneous continuum, right? It behaves as if all of this is one thing, and that all movements and changes are just ripples in this continuum. So that's an appropriate model if you have a continuous fluid like this. That is not the only fluid that occurs in chemical engineering in particular. So of course you can have fluids which are really collections of larger particles. So if you have particles on the order of even microns, which is much bigger than the scale of molecules, right? Molecules are on the scale of 10 to the minus 10. That's where really you do have a continuum for all practical purposes. When you start to get to the micron scale, which is 10 to the minus 6 meters, then you really can start to see these things. So at 10 to the minus 10, maybe something like around 50 times 10 to the minus 6. This is really on the order of a dust-sized particle. So you can start to see it. In this case, you have discrete elements, and it's not the case that changes in the one automatically transfer to changes in the other. In this case, a change in this molecule, it's going to collide with the neighbors at some stage, and so it's going to, if one is at a high vibration state, it's going to affect the whole continuum. Here, not really. So in a discrete space, there is another field of study which is called population balance modeling. So this is an important area for chemical engineering. For some reason, it's not taught in most curricula. So I'm not aware of any undergrad programs where they do teach this, but this is the other half of the missing part of chemical engineering. So remember, this whole course is in a way your introduction to the theory of chemical engineering. So there is somewhat of a bias towards the continuum modeling that we've been doing, and that's what's presented in this course. But be aware, there is this other field of population balances, and that has to do with more discrete elements. But you'll find in most of the courses in the curriculum, the bias is towards a continuum. When you meet me in the reactors courses another time, we will deal with some population type elements. So that does arise naturally in chemical engineering, but it's not taught under the correct and rigorous way to study this is population balances. So when you have time during the breaks and so on, look up population balances. It's another very useful side of chemical engineering. But continuing with this, so this, in a sense, is the framework, the theoretical framework that we have established. Maybe just to pause there, any questions or comments so far? Okay, and now continuing here, of course, we've got these and we'll work through these examples in more detail and so on. And then I showed last time about using the deriving this from a fundamental theorem of calculus perspective as well. So what we'd like to look at now is just how does one also solve these equations? And this solution of differential equations, this is not really part of the course either. This is more pointing out in the other parts of chemical engineering what you'll be doing. So we'll just take a quick browse look at this. So if you have an equation of this form, then typically we decide on a set of coordinates, and then we decide which coordinates matter. So if, for example, here only x matters, then our equation simplifies down to this form. And then the way we solve this equation is by converting all these derivatives into numerical estimates of those derivatives. So of course you can estimate a derivative using this formula, right? The gradient of c with respect to t is of course the change of c divided by the change in t. So that's an estimate of the first order derivative. And you can define left side and right side derivatives. So if you are working between I and I minus 1, or between I plus 1 and I. So those are left and right side derivatives. And so by averaging the two, you can get better estimates of the derivative. And then you can estimate the second order derivative, the second derivative as the derivative of the derivative. And so if you take the derivative itself, the difference in the derivatives at the two different points divided by the change, and then you substitute what we had here. So in the first order case, we have this numerical estimate of the derivative, which we simply substitute in there. And then if you stick all that together, you get a formula for the second derivative. And then you go ahead and substitute that into your equation. So the rest of it doesn't explain it too much. Just to sketch out the way we solve these equations. You can imagine if, for example, it's c and x, and we are solving some equation dc dx is some function of c and x. Then if we imagine starting at some point here, then that defines a starting concentration and a starting x value. So we simply stick those numbers in here, and then this function will give us some number. So it's going to give us a number, and this number is of course equal to dc dx. So that is telling us how the concentration is changing near this point. It's telling us dc dx, the gradient of c with respect to x looks like this. And then what we do is say, well, if that's true, then let's step forward a small amount. And so we get to a new point here. This gives us a new value of c. And we say, okay, we've stepped forward. Now we are at a new value of x and a new value of c. Let's stick those in again here. And then that's going to give us yet another point. So we apply the new gradient, and then that gives us another point here. And then we step forward again. And so we keep doing this, right? We reach a new point, stick it in, and then that gives us a gradient. We step forward along that gradient, And we keep doing that until we get a solution. So we get a solution that tells us how the concentration is changing along the X direction. And so you can repeatedly do that. And there's this example here. So you just step forward using this kind of approach. And here's an example. This does relate to one of the problems we had with the diffusion. And you can see here, when you read this equation, you can see your convection part. So here's dc dx, right? This is delta C and delta X, and then U times dc dx. And then here you can see diffusivity, and this is the second order derivative of C. So this is d2C dx squared, and this is diffusivity times that. So this is nothing but the diffusion equation that we are familiar with. So the Python code is here. You can copy that out and run that. And then if you do so, you get the solution. And if you look at the solution, we can see we've got concentration here. And then we are looking with the X position along here. So we started out with none of component C except at this point here. And then as time went on, because we had a high concentration up here, it starts to diffuse into the fluid at these other X positions. And so we've got the concentration rising as time passes. So that is all solved using the same method that we just talked about. So if you look here, we are doing nothing but evaluating the derivative, and then we are stepping forward that derivative as we described earlier. So don't forget that it's as easy as this. And I know looking at it like this, it looks complicated, but if you have the patience to step through each thing, it's all really very simple. So later on, when you meet PDEs and you start applying them to complicated spaces, just remember it is all as easy as this, right? So that's how we solve these things practically. And as we showed in one of the earlier lectures, this is, of course, a very simple space. This is along a straight line in X. But if you have a more complex geometry, like we showed the aircraft or the race car, you can define little volumes. And the calculation for all that is, it follows the same principle. We estimate derivatives, we step forward in time, and we estimate how the concentration and temperature and pressure and all of that, how it all changes across the space. So it's nothing but that. So that's how we can numerically solve these equations. Right now, what we want to talk about today are the analogies among these equations, because back when people were trying to build reactors, they didn't have available all these numerical methods. Even a simple one like this, even to be able to solve this simple equation and get this simple solution, this was kind of unthinkable maybe 50 years ago, right? To have the computing power to do this, well, even to program a computer to do this was exceptionally difficult, let alone having a computer with the memory to process the data. And they wouldn't even think of being able to render a surface like this that you could look at. So they didn't have any of this available back then. And what was available was the brain power, right? People used their brains back then. And what they came up with was to say, well, we can see that all these equations have this kind of similarity. And it's the same similarity we've been talking about in the first part of this lecture. We can see there's convection and diffusion and accumulation. And so using our brains, we can see, okay, then the equations have that rough kind of structure. So can we, first of all, try to find some dimensionless groups? And so dimensionless groups, that's one of the, how can I say, that's one of the favorite methods in the toolbox in maths and physics, where you look at a complicated equation and you say, okay, fine, it's complicated, but is it not possible for me to rewrite this equation in a form where things are normalized out? So instead of writing concentration, I'll write concentration divided by initial concentration, just to make it dimensionless. And the thing is, when you start doing that and you start finding dimensionless groups, right? These are not yet dimensionless, but you can see some kind of ratioing. So I'm trying to divide some of these things out. So when you start finding things that begin to look like dimensionless groups, you can start to ask about relationships between these concepts. So for example, in our mass balance, right, this one, you could ask, well, what about competition between these two terms? What if velocity is much greater than diffusion? Does this equation become simpler in any way? And once you can understand that, or once you can figure that out, then you can start to think of a different way to solve this equation. Isn't there a much simpler way to solve this equation? So let's think about that. Let's think about a simple situation where we have that the velocity part, so we know it's of the form u times ca. What if the velocity part is much greater than the diffusion part? So the diffusion part is, of course, this. Right, so if that's the case, then our equation becomes much simpler, and that means we can effectively ignore that part. And so we can then say simply the rate of change of concentration, dCA dt, is approximately equal to minus u dCA dx. And this equation is much easier to solve. And in fact, if you really use your brain around this, you'll realize, well, I don't even need to do that much. All I need to do is recognize that in my space, I do have a velocity part that's affecting my behavior. So I'm feeding at a certain velocity, and the rate of change in any control space there is affected only by this velocity. So if it's only affected by velocity, I can develop a much simpler description of the changes across this space. And so if, for example, if there's no other change going on in the system, then I could say simply that eventually my process is going to reach the same concentration as I have coming into that space. So these are the kinds of simplifications that we can start applying if we start looking at the relative amounts among these factors. So number one, if velocity is much faster than diffusion, then we can say the bulk of the change that's happening in concentration is going to be just due to flow. In other words, there isn't enough time for diffusion to happen significantly that it's going to affect our result. So we can significantly simplify our equations, and we can start to predict what the solutions will look like. So that's part of the origin of this set of analogies that has taken root. So we can look at competition between terms in the same equation. And we can also start to look at competition among the terms in the different set of all these equations. So for example, you could look at competition between convection and conductivity, or competition between convection and the viscous flux. So that is the origin of these dimensionless groups that have emerged in the literature. So the Peclet number is the one we just talked about. It's the competition between the convective flux and the diffusion flux. And so if your Peclet number is extremely high, then your convection matters much more than your diffusion. You can also compute the Reynolds number. So the Reynolds number, again, that's defined as the competition between convection flux and your viscous flux. So how fast is your fluid diffusing its velocity, right? Viscosity is how fast your velocity diffuses away. And you see, with the Reynolds number, you can actually then start to identify specific flow regimes. And we have this, this criterion that for a Reynolds number that is greater than 2,100, that we get the onset of turbulence. And so if it's less than 2,100, it's laminar. And that is quite a crazy general statement to make. It's saying that if the Reynolds number, du rho over mu, if that is quite large, then your flow is turbulent. So you have this kind of a kind of flat profile because it's in turbulent flow. Again, like we talked about the other day, if you have a tap and you have a high flow rate through your tap, then you get this turbulent flow coming through. Whereas if in the same tap, you use a lower flow rate, so you don't open the valve fully, then you get this kind of laminar appearance here. And you can use the Reynolds number to detect when you get this onset of turbulence. So beyond a certain velocity, you see the onset of turbulence here. And that Reynolds number is quite easily estimated. So for example, in the case of water, we can get the viscosity. So the viscosity of water is quite well defined and documented. Then this L here, we'll talk about what these L's are. But if that's the pipe diameter, and then if that's the velocity, and we know the density of water, then all these can be estimated quite easily. So you can get the Reynolds number fairly easily. And that means no matter what kind of situation you have, so whether it's your flow in some kind of pipeline and you are considering using different diameters of pipeline, or if it's a big reactor, and again, you've got some kind of fluidization or flow through there. So you can have ridiculously different situations, but now you have one criterion. So in other words, the Reynolds number is exposing something fundamental about all these different situations, and it's helping us to detect the onset of an important flow regime. So that means we are able to figure out how the fluid is going to behave, and we can design around that. So for example, if we knew that we wanted turbulent flow because that gave us good mixing or something like that, then we know that we have to maintain a Reynolds number above this range. And because Reynolds number is du rho over mu, so that's diameter, velocity, density, and viscosity, right? Then you can't really change the viscosity of the fluid or the density of the fluid. You can definitely change the diameter and the velocity. So if you want your fluid in a particular flow regime, you have this kind of power to change it. So, so that's one of the tremendous advantages by these methods, right? By using dimensionless groups. So you could think about trying to solve this. Imagine the complication of trying to model or simulate even turbulence like this. And there are attempts to do that. But it's going to be so complicated to try and model every single packet of fluid. Instead, you have this nice practical Reynolds number, which immediately tells you whether it's going to be turbulent or laminar. So that's a giant step forward. And the Reynolds number in particular is something that has propelled chemical engineering forward by decades and decades. The original chemical engineers did not have to wait for us to come up with computational fluid dynamics and this rigorous theoretical framework to construct something like a a distillery or something like that. So that's the Reynolds number. The Sherwood number, that's the competition again of the, well, this is a competition of the mass transfer and the diffusion rate. So mass transfer, remember, this comes from a simplification of diffusion itself. That's an approximation. We presented this as an approximation to diffusion. But if you take the diameter, for example, of a pipeline, and then that ratio tells you how much, like a simple mass transfer, it tells us something about the extent of the mass transfer that we can accomplish there. So that's a Sherwood number. A Nusselt number, this relates to the convective heat transfer and the conductive heat transfer. So I would say the Nusselt number is similar to the Peclet number, right? The Peclet number, that was the competition between convection and diffusion in the mass sense. The Nusselt number is the competition between convective heat transfer and conductive heat transfer. So it's like the energy analog to the Peclet number. So if you have a high Nusselt number, that means your fluid is not conducting fast enough, and that the most important things that matter are the flow in and out of the space. So the flow is going to determine the heat transfer. On the other hand, if it's very low, then your conduction is going to predominate, and you can look at the conduction terms to figure out how the temperature is going to change across the space. The Schmidt number, that's the competition between viscosity and diffusivity. So in this case, we are looking at the diffusive parts. So the competition between viscosity and diffusivity. So does the viscous drag outweigh the influence of the diffusion of molecules? So you can imagine that has important applications again to mass transfer. And then the Prandtl number, your viscous drag, how does that compare with the thermal diffusivity, with conduction? And well, that's a conduction that's normalized by the capacity. So all these help us figure out where or what regime we are in. It helps us figure out what's the most important factor in that's governing our current system. Okay, and then here are shown some of the original solutions, or some of the original attempts to derive relationships among these. So of course, there have been attempts to develop relationships among all the variables. So you can look up the Reynolds analogy, the Blasius solution, and this one is known to be quite accurate, the Chilton-Colburn analogy. So in all these relationships and analogies, what we are doing is relating dimensionless groups to each other. So you can see the Prandtl number here, the Schmidt number there, and so on. So these are correlations among our constants. So we are not even trying to solve equations anymore. Now we have simplified the whole thing down to just relating all the constants involved in the equations to each other. And if you look at some of the examples in the set of notes, you can see here there's a problem. Air is flowing over the surface. There's carbon dioxide subliming around, and the viscosity is given. And we want to know what's the mass transfer coefficient. And if you think about it, this is a crazy thing to ask, right? If you look at all the data that's given here, a lot of it is not obviously related to mass transfer at all. But through this great power of analogies among momentum, heat, and mass transfer, we are able to relate the seemingly unrelated constants to each other. And so this is a way to extend our estimates, or it's a way to extend what we can do with the available data. So quite often in engineering, we only have a very limited amount of data available to us. Now, with these analogies, we can actually find relationships and estimate constants that we don't have measurements for. And with those constants, we can then go ahead and solve our balances and get to the answers that we are looking for. So that introduces this concept of analogies among heat, momentum, and mass transfer. And in the next session on Wednesday, we'll cover some examples around that. Any questions or comments there? Okay, if not, then